Let's invite up our next speaker, Jeremy Freeman. Jeremy is head of research and engineering at WattTime, an environmental tech nonprofit that empowers all people, companies, policymakers, and countries to slash emissions and choose cleaner energy. An excellent thing to do for sure. And is the electric power sector lead for Climate Trace, a nonprofit coalition created to create the world's first comprehensive accounting of greenhouse gas emissions, based primarily on direct, independent observation. So thank you so much, Jeremy. Come on up, and please join me in welcoming Jeremy.
Thank you, Kyle. So I wanted to start and introduce our journey into using remote sensing. WattTime got started because we came to understand that the power that you use in a day-to-day basis, like if we turn on a light right now, some power plant responds to generate that power. And that power can be cleaner if it's a clean plant, or it can be quite dirty if it's a coal-fired power plant burning. So we developed this automated emissions reduction program where we analyze real-time emissions data from different parts of the power system and estimate what the marginal emissions rate is. Like if you turn on your power right now, how much additional CO2 or greenhouse gas emissions are going to occur. And we develop an API that then powers various different IoT devices, and more are growing to, if they can shift their power demand back and forth to operate at a time when things are cleaner, that's a net improvement in greenhouse gas emissions. That data can also be used to understand the impact of siting your renewable power plants. If you put them in an area where their impact is going to be higher because they're going to reduce more emissions, that's more impactful, so you can make some decisions there. But to do that work takes great data. It needs to be comprehensive, hourly, at a facility level, accurate, unbiased, verifiable, near real-time emissions data. And because greenhouse gas emissions are a global problem and the solutions are global solutions, we need to do this globally. The problem is, for us, most countries don't have such data. We heard earlier in the conference, the EIA. So you look at our map of the United States, there's lots of detailed data available. There's a similar type of environment where there's not as much data available in Europe. There's also data available from different power providers in Australia. But there's a vast part of the globe, and there's a vast part of greenhouse gas emissions that aren't covered with such data. And as we zoom back and said, well, just can we characterize what's going on in a certain part of the world, we found that the average country inventory for greenhouse gas emissions is 11 years out of date. There's some that are great, there's some that are quite old. A lot of the data is high level, so you see national totals, not subsectors, not individual asset level. You can see incomplete or undercounted data, as we just heard about, and a lot of it is through self-reported information. And in some places, that self-reported information is probably quite high quality. Other places, it's some sort of a paperwork exercise, and data is just reported. So we looked to the sky, and flying above us are many, many, many satellites. And we started working there and got a Google AI Impact Grant to try to study what's going on with power plants using remote sensing. And through all that work, that led us to actually understanding this is a bigger opportunity, and it's also a bigger challenge, understanding greenhouse gas emissions globally. And we became one of the co-founding members of Climate Trace, which is an organization, initiative that's working to gather partners and different organizations and collaborations from universities, nonprofits, tech startups, environmental groups, and other for-profit organizations to try to track what's going on with greenhouse gas emissions globally, where we're trying to boost the comprehensiveness, enhance the transparency, and spur accountability for greenhouse gas emissions. What we work to do is produce a countrywide and as well as an asset-level emissions inventory, so down to the individual asset level for the greenhouse gas emissions across basically all sectors of the economy and the natural systems that are interacting with the greenhouse gas emissions. This platform, currently what you see online, if you go to climatetrace.org, will show you 2015 through 2022 emissions by subsector for various different greenhouse gas emissions. And then with asset level estimates for the largest emitters in different sectors. This is a group of collaborators, including Duke University. Kyle talked a little bit about some of the work on buildings there. Elizabeth is also going to talk about some work that was done for road transportation. And I'm going to talk a little bit more about what we're doing for power plants. This website basically is a process that we're going through. It's developing this inventory. And if we look here, there's a website where you can go and look at, select which region you're looking on, which year, and which greenhouse gases, and which sectors you're looking at, and see them at a country level. And then also trace down to an individual area and look at what are going on with power plant emissions, with steel and refinery emissions, land use emissions, and things like that. And with the data that's currently on the website, you can see here, these are the largest emitting assets in the world. And you see the Permian Basin, very relevant to our last discussion, from methane emissions there. And you see at the bottom of the list here, number 4, Taichung Power Station. The general process that we're doing at Climate Trace, and I'll go into more detail with power plants, is not every satellite out there is actually measuring the greenhouse gas emissions, like the satellite we just heard about that's going to be launching. So a lot of times what we're doing is looking for a signal that's proxying these emissions. So it's very common to be able to use the activity level of, say, a power plant. You may not be able to measure how much CO2 emissions are coming out of the power plant stack, but if you can assess how much generation there is there and what fuel it's burning, the carbon intensity associated with that activity is pretty straightforward to understand. There's error bars on it, but it really constrains the problem. And it really opens up the opportunity to use many more sensors because you're looking at activity. So you'll see a couple of examples here with oil and gas. You're looking at flaring data. You can see some thermal signals associated with that. You can look at, for rice paddies, another emitter of greenhouse gases, especially methane. You can look at the patterns of where is the rice being grown, how is it being flooded, what are the different activities there, and how that would lead to the emissions rates. Generally, we take that process and train models and then estimate that activity globally. Currently, we're seeing basically all the countries and jurisdictions in the world that we're tracking, and currently what's up there is 70,000 facilities and other types of assets, but there's a big update coming out in preparation for COP. So over the next 2 months, if you take a look, you'll see a big expansion in our capabilities. The idea with Climate Trace is that it's trying to be independent, timely, and comprehensive, which is really a big step forward in what data is available for a comprehensive view of greenhouse gas emissions over the globe. So more specifically, the work that we're doing, the team that I'm working on, is inferring CO2 emissions from power plants using satellite imagery and machine learning. You see a long list of co-authors on this work. It's been the work of many people over a fairly long period of time. Why is it relevant? If you look at the global electric power sector, it's somewhat over 25%, somewhat over a quarter of the greenhouse gas emissions are coming from the electric power sector. In our study, the way it's broken out here, it would be the biggest. As you combine different sectors in different ways, you can maybe argue it's maybe not the biggest, but it's one of the biggest. And when you look at this map, when we think about greenhouse gas emissions from power plants, we kind of naturally jump to coal-fired power plants. They're amongst the dirtiest. They're very prevalent in different parts of the world. And this plot here is not directly driven from WRI data, but that WRI data is very similar to look at a lot of coal-fired power plant in the U.S. that is coming down. A lot of coal-fired power plants in the Asia area. And when we look at that map that we had before, like where you have great data, we can probably, Climate Trace is not necessary, remote sensing is not really necessary here, to understand what's going on, but it is necessary in the rest of the parts of the world because the data is just not available. So we've been talking about remote sensing, so I thought it'd be interesting to kind of show 3 different remote sensing platforms that use visual and other data. So I don't know how many people here have worked with remote sensing. There's a quick show of hands. How many of you all are familiar with Landsat? Sentinel? Planet? It's pretty interesting to see side by side. This is real data of a power plant, and we're looking at, in Planet, you can see structures here, but the power plant's right actually here. And it takes a bit of a trained eye to see it even in Planet data at this scale. If you zoom in a little bit, you can kind of see what's going on. We move to Sentinel, a little bit blurrier. If you kind of really pay attention, you can see what's going on. And Landsat, if you really pay attention, you really know what you're looking for, you can see it. But the interesting thing with power plants is their operation changes day to day. So when it gets really cold, we need more, generally speaking, we need more electric. When it gets really hot, we need more electric. It's nighttime, everybody's asleep, we've turned all the lights off, we need less electric. So the activity level of power plants in general changes on an hourly pattern, a daily pattern, a seasonal pattern, and it also varies a bit around the world. So a really important aspect of trying to understand how power plants are emitting CO2 into the atmosphere with remote sensing is how quickly you revisit. So Landsat is a very interesting satellite. It has lots of capabilities, but basically you can see the world kind of every 16 days if it's not cloudy. If it's cloudy, you got to wait for the next 16th day. Sentinel-2 has a pair of satellites orbiting, and the way that orbit pattern kind of gives you a view of the world kind of every 5 days. And PlanetScope has a constellation of satellites, and you can get basically a daily revisit anywhere in the world with that data. But you're kind of limited to what bands you can use in that sense. So our general approach for monitoring power plants is we take the power plant imagery, so as many times as the sensor comes over, and this cross section of different sensors, we align that with where we have training data, where you can identify the power plant with reported generation data. And we look at what aspects of that power plant are visible from satellites, from remote sensing, that are somehow tied with its activity. And I'll show you an example here, and we'll describe it in a little bit more detail in a moment. But you can see these red boxes. These red boxes are drawn around two different structures on this power plant. It's a coal-fired power plant. And those are, these large cooling structures here are called natural draft cooling towers. When you combust coal in a power plant, depending on where you are and what type of power plant it is, maybe 30 to 40% of that energy actually turns into electricity. The rest of it is some sort of waste energy. The vast majority of that is from cooling the condensers. And in classes of power plants, that cooling is done with evaporative cooling. And so you can see these small plumes of clouds coming out of the top of that cooling tower. The other aspect is up here with these flue gas stacks. When you burn coal, there's a lot of sulfur in the coal, and not everywhere in the world, but in large parts of the world, you have to clean that up with a wet flue gas desulfurization system, and amongst other systems. And both of those give off a visible plume that we can see from satellites. The basic overall methodology here is we start with a power plant inventory, like we saw from WRI yesterday, amongst others, to understand where's the location, what is the fuel, what is the cooling technology, what are the pollution control equipment, and say, is this a power plant that we can make an estimate on? We geolocate the infrastructure, the location of the natural draft cooling towers and the flue gas desulfurization stacks, and then line up satellite imagery and align that with plant level generation as well as weather data, because the weather plays a role in what you can see from the satellites. And then we build what we call a sounding model, which is a sounding we call is like one single image. So if we take a single image of a power plant, and we can run it through what we call our sounding models and say at that given point in time, is the power plant off or on? And if it is on, to what level of power is it running? Is it running at 10% power, 50% power, 100% power for its capacity factor? That data generates a time series of observations. And we put those through a second level of machine learning called we refer to as a generation model, which takes all these different soundings from the different sensors with the different models we would use over all the time and put that together and make an estimate of how much did that power plant operate over the last 30 days. From that, since we're not using a direct measurement of CO2 emissions, we're using a carbon intensity model to model for this particular power plant, if you're burning 1,000 megawatts, how much CO2 is coming out at that given time. From that, we estimate the emissions. Here is a couple of just different slides to show kind of what it looks like a little bit more zoomed in. But the really interesting aspect of this is the models. When you go and apply these, there's just 3 different power plants in India where there's not as good a data as available in this part of the world, in the western part of the world, in the US in particular. And go back and look at our generation models as applied over time from January 2018 to January 2021. And you can see basically this is a trailing 30-day average of what our estimates are for relative emissions. And they line up quite well with some details that were going on in India where there's a period of low demand. The COVID lockdowns, you can see, affect all 3 power plants quite dramatically. And then when the farmers' protests were going on, you also see a dip in how much generation was going from the power plants and the associated emissions. Our models can differentiate kind of high and low utilization. It'd be great if the satellites could say this is exactly what's happening. But we're basically in a situation for the natural draft cooling towers. Our relative RMSE is on the order of 14%. And then for the FGD, which is a little bit more of an interesting phenomenon, we're seeing kind of around 20%. You can go to Climate Trace and see all these data put together. But since we're talking about remote sensing, I'll take my last couple of seconds here and talk about a couple of different sensors that we're working on. One is using the thermal measurement. So there's a lot of satellites out there that are trying to measure land surface temperature. And they're looking at that kind of globally, but you can actually zoom in and look at small levels of the power plants and see where you can see emissions associated with thermal emissions from the cooling systems. There's another satellite called EcoStress where you can do this. You can see this data is much coarser and kind of highly pixelated. There's going to be a lot of work to try to pull out how you get this signal that's kind of repeatable and reliable that you can apply globally. And then perhaps some of the more interesting stuff is actually measuring some of the direct emissions from power plants, both NOx, which is co-emitted with CO2 at power plants, as well as actual GHG measurements of CO2 emissions, which, as we heard about in our last presentation, have some interesting possibilities and some interesting challenges. So I look forward to the discussion, and thank you for the time.